Hello everybody and welcome to Control System Analysis and Design. Today we're going to be creating a PD controller for this closed loop feedback system that we have. So the first thing I'm going to do here is just kind of to visualize what we have going on. I'm going to do a root locus plot. We have a pole at the 0, at -10, -10, and at -20, -20 right there. And then if you fill out this root locus plot like this, and maybe you kind of find out where your asymptotes are, they're going to be something like this. Okay, so that's generally what this system does right here, as it sits right now. But we need to add in a controller in order to change its settling time by a factor of 4. So a PD controller is of the form C of S equal to K of S plus A. So PD controller gives us another 0 to add somewhere on this line. So say we add the 0 right there. This 0 and these poles define where the number is going to be where the TS that we want is. So imagine if you were to graph this in MATLAB and you were to find a TS of this point right here, which gives you 20% overshoot. You want a factor of 4 of that, so you need to come straight out here. So our new TS, 4 times TS original is going to be out here somewhere because that diagonal is the line of constant settling time within the complex plane. So what you can do is you can take this function, stick it into MATLAB, and have it do an R locus of the system. Use that command, and what you'll be able to do is you'll be able to get on a locus plot and then run along the line, and you'll be able to pull some values off of this that we'll be able to use. So if you did that, if you use MATLAB, K is equal to 1.16 times 10 to the third. The poles are equal to -3.19 plus or minus J6.24. or 6.24J, whichever. It doesn't really matter. Alright, and then this is where the OS is equal to 20%, because that's where all systems have to operate, is at 20%. Okay, and then zeta is going to be equal to 0.457. Now you have to calculate omega n here real quick. And omega n is negative zeta omega n. Excuse me. And if you do that, you'll actually find out that it is equal to -3.19. Because you can actually just pull omega n straight down from here. Because this is omega n when you have these the complex equation basically. Omega n is the real pole. Alrighty, and then omega n, omega d. Wait a second, I made a mistake. This is omega d. Sorry. Wait a second. Yes. Right. You use this value, you bring it down here into this equation, and then you multiply by zeta, and you'll get the value that you want. So omega n will end up equaling 6.98 when you do that all out there. And then your settling time, also another equation, 4 over zeta omega n, which is equal to 4 over 6 point. Excuse me. Let me grab my eraser. This is omega d. I'm sorry. Apologize for that. Omega d is equal to omega n. And then you use omega n down here, and it is equal to 4 over 3.19, which is equal to 1.25. Just like that. Okay, so you've got your basic values for the original function. Now, if you want to find out what the values for your new function is after the compensator, you have to figure out what this pole is going to be once you put in this 0. So you still are going to have an OS of 20% because that's a given. You have to have that. TS is the new TS is going to equal 4 times TSO. So in this case, it's 4 times 1.25. So 4 times 1.25, which is then equal to, oh no, yeah, we're reducing it by a factor of 4. Not increasing it by a factor of 4. So divided by 4. Divided by 4. Wow, I'm just making mistakes all over the place. Since we're reducing TS by a factor of 4, you divide by 4, and this will give you a settling time of 0.3135 seconds. So that's our new TS that we're shooting for. Now, if you look at zeta, some of these values are going to be extra that we don't really need. But since OS is the same, zeta is you calculate from OS equal to 100 e negative zeta pi all over the square root of 1 minus zeta squared. You could do this calculation, but since OS isn't changing, it's 20%, your zeta is going to be exactly the same as it was over here. So zeta is going to remain 0.457, and you can just jump right to that. And then you can calculate omega n the same way we did before, which is omega n over 4 over zeta ts, not exactly the same, using the ts equation, which is equal to 4 all over 4.457 times 0.3135. And that will equal 27.91. And you'll notice that 27.91 is 4 times what omega n was over here, which is 6.98. So if you can do this calculation, but really it's just easier. Oh, omega n, the natural frequency, is going to be 4 times what it was back here because we're compressing it basically by having a faster TS. So this is 4 times omega n. Then if you wanted to do poles, you could, what you can do is you can go negative zeta omega n plus or minus omega n square root of 1 minus zeta squared j. But again, that's a long way around. Since we know that we have a proportional compensator of a certain magnitude larger, you can just say, oh, well, we're going up along this line. Both of these values are linearly going to become 4 times greater than they were before because we're on this line. So you can do this math, or you can just multiply the poles that we had from the last one that you pulled off MATLAB by 4. So you'll end up with negative 12.75 plus or minus 27.91 square root, oops, sorry. That's solving a little too much. 24.825 J. And these are our new poles. So this is the location of this point up here. So I'm going to redraw one more line, another root locus plot with our new system here. I'm going to draw this up here. I'm going to put negative 10 right here, negative 20 right there. Oops. We got an x there, still an x at 0. And then here at negative 12.75 and at 24.83, I'm going to round that up. We have this new new set of poles up here. And if we do our root locus, it's going to be something like that, something like that. Actually, it's not going to be something like that. We're going to have a 0 somewhere along this line that we're able to use the angles of each one of these to find what that 0 is going to be now. Okay, so we know that we have this point here, but we need to figure out what these angles are. We need to triangulate its position using the positions of these poles with respect to it. So we have this point, we have this point, we have this point, so you can use trig to figure out the length of each one of these, and then from that you're able to figure out what the length where the 0 is supposed to be on the axis so that it also contributes to the location of the pole. So I'm going to go ahead and add in our compensator now. We're going to put the compensator in the forward loop, so it would be like putting the C right here or something like that. So you're going to end up with K of S plus A all over S times S plus 10, S plus 20. And this is the open loop system. we haven't closed the block diagram or anything like that. We just added in the compensator. And this is what you get. You multiply it through all, and you all get what you need. Now, so we need to find A, which is the location of the 0 on the real axis. So I'm going to get a whole new sheet of paper to do this. In order to do this, you have to find, if you're drawing the lines from this point to here to there to there to there, these are just lines, you have to find theta 1, theta 2, theta 3, and theta 4. Actually, when I did the calculation, I might have switched these two. But basically, just find the angles of all of these, and then you're able to find the length and the sides, and then the final equation that you do, you'll be able to find out what the length of this is. So it'll become clearer here in just a second. So for theta 1 is equal to 180 degrees. Now the reason we use 180 is because the larger angle is over here, but we really need the smaller angle in order to get the right triangle here. So you use 180 minus whatever the value of this is. And the value of this is minus the tangent, inverse tangent, of 24.82 all over negative 12.75. Okay, so how did I get that? Well, if you're looking up at this, you've got our new point up here, and then you've got our pole at the origin. We know that this point is something like this, along the x-axis, just like this. And you're trying to find this angle, or I guess this angle too. What you're going for is, what we have is the opposite and the adjacent right here. And we know that this is negative 12.75, negative 12.75. And we know that this is 24.83, which is what we got when we found that point. So in order to find this angle, we just take the inverse tangent of these, opposite over adjacent. Basic trick. So if you do that and you do out all that math minus the 180, because again we're just technically taking the inverse tangent of this. Well, no, we're taking the tangent of this angle and we're trying to find this angle. So this is going to be equal to 117.19. Okay, so that's how you get that one. Okay, so now for theta 2 is equal to 180. For the same reason, we're trying to find the inside angle, so we got to get rid of all this stuff out here. Minus the tangent of negative 1 of 24.82 all over 12.75 minus 10. Again, why do we do that? Well, looking at this new one, I'm going to draw this solid here. We got x right here. This is our original x that we just did a second ago. This one's at negative 10. This one's at negative 12.75. And then 24.8. So we're trying to find this angle. We've got 12.75 minus 10. The reason we use the absolute value of it because we're just trying to find the magnitude of this. We don't care whether it's positive or negative or anything like that. In fact, the negatives create a lot of danger for you if you're doing that. So I technically take the absolute value of these. And then you have the height again, and then you just solve it through just like we did the last one. And this will equal 96.32. Which makes sense, because as a sanity check, that one should be smaller than the one you did a second ago, because the angle's getting closer and closer and closer. So we're at 96 almost. We're almost at 90 degrees when we're just 2 apart here at the base. This is exaggerated, but it's really something almost like this, if you were to draw it to scale. Okay. So now, for theta 3 is equal to the tangent negative 1 of 24.82 all over 20 minus 12.75. Now, why don't we have a 180 here? Well, again, if you're looking at the 12.75 and we've got our negative 20 over here, then you've got it over here like this. So you don't have to subtract 180 in order to get the inside angle. It's already given to you. And I switched the angles around. Theta 3 is the one from the pole at negative 20. But it's not that big of a deal. But if you solve it, you'll get 73.71. Just like that. Okay. So now we need to find theta z. The angle that the 0 is at. Okay. So the equation that you use for this is theta z is equal to the sum. Let me make sure I tell you the right story here. Negative theta 1 minus theta 2 minus theta 3 is equal to 2n plus 1 times 180. This equation, what I got this from, is the equation of the sum of the zeros, sum of the thetas of the zeros, minus the sum of the thetas of the poles is equal to 2n plus 1 times pi. So this is the equation where I got this. So we're trying to find the theta 0, so we take everything on the other side, and you're able to solve basically right off the bat here. Because at this point there's technically no 0, so you're able to just go with negative, negative, negative poles equal to this. So you solve that out, and you get theta z, split that out, do some solving, which is equal to 2n plus 1 times 180 plus 287.23, which is the sum of all these angles up here. Bringing all these down. Okay, so taking that onto the other side, just like that. And so then coming in here, going a little bit further, theta z, I'm going to go ahead and use n equal to 1 here. The n that you use is really arbitrary, but you normally just want to use a number that's n equal to 1, or n equal to 0, or n equal to negative 1. I actually used n equal to negative 1 in my notes here to ensure that the value that I get here in a second is the value that I need. So 107.22. Okay, and this is a reasonable value because, again, if you're looking back at our root locus plot, well, I drew it back over here so that theta z would be a smaller angle, like, I don't know, 60 or something. But in fact, the 0 is over here, so our theta z is 107. Okay. So we have our theta z now. So that's great. But what do we do with that? That gives us our angle. We still don't know the location on the x-axis, which is what we were trying to find in the first place. But that's a fairly easy thing to do because we know that y over x is equal to tangent of theta z. And we basically go backwards from what we were doing with all this stuff. We were trying to find the angle here, but now we're going to try to find the x here. So x is equal to y over tangent of theta z, which is equal to 24.82 all over tangent of 107.22. Okay. And this value is going to get equal negative 7.69 is equal to x. Alright, so that's the length of the leg of the triangle. But now let me show you something that you got to watch out for. We have a 0 right here. The new pole is up there, coming down here, coming down there. What we just found was by using this angle right here, was the height is 24.82. But what we just found was this little section right here. This is not the thing that we care about completely. We have, this is the point negative 12.75. But we found out that the triangle is negative 7.69, or 7.69. It's basically an absolute value. Since we took this angle, it's a negative. But we still have this piece over here in order to get the x value that this is actually sitting at. So in order to finish this off, we need to do 12.75 minus 7.969. Why did I do that? Well, I was doing absolute values because this is a 12, this length is 7.69, and I want to get this length. So that's how I have to do this. So this length right here is going to be equal to 5.32. And that is equal to our A. So we just found the location of the 0. It gives us the pole we need in order to get a 20% overshoot. Wonderful. So we have, if we go back to our transfer function that we've been working with, we have k of s plus 7.69, or no, not 7.69. Just made the error that I told you not to make. 7.69, 5.32, all over s plus 10, and s plus 20, which is equal to g of s times our compensator c of s. So, this is a partial answer. The trouble is, we don't know what this k is, and this k is part of the compensator that we just put in. Find k. This is the last part of the problem. Find k. So what we're going to do with this is use the open loop system. kgh is equal to 0. Kgh is equal to -1. Now we're solving for k, so you can just go ahead and take k equal to -1 over gh. And actually, you can take this even a step further and take the absolute value of both of these, and you get 1 over gh, basically, absolute value. Okay, so now what is gh? Well, we know that g is equal to k all over, what is it? K over s plus 10, and s plus 20, just like that. So now we, and you can actually change this since we have a k taken out. K all over s of s plus 10, s plus 20. Oh, no, not k. 1. 1, right there. So, this k we just factored out by dividing this piece over here, because this was the open loop system that you multiply all around. If you divide by g, then you leave the k behind, and you'll have a 1 there. So now, we need to find out what this g equals when s is equal to -12.75. This is the location on the real axis where the pole exists, so we put this in for s. Okay, so g equal to 1 all over -12.75 all over -12.75 plus 10, and -12.75 plus 20. Kind of scratch that in there, but you get the idea. Put s, -12.75 in for s. Then you solve this all out. Take that value of g, put it back up into here, and you get k is equal to 254.2. Give or take 2 or 3, depending on how accurate your calculator is and how many decimal points you took all these and the divisions and everything else. But you find this value, put it up here, divide 1 by that value, and you get 2.50, this value right here. Which, if you really want to just kind of not be redundant, you can just take this denominator, multiply it out, and that'll be your answer up here. But just to be complete, and if you ever have an h or anything like that, you need to also include this. But so your k is 12.75, so your compensator is now going to be equal to 254.2 times s plus 5.32, which is the location of the 0 we need, and this is the gain we need in order to get the pole. Okay, and then so if you want your final transfer function, it's going to be 254.2 times s plus 5.32 all over s of s plus 10 times s plus 20. That is equal to g of s, c of s. And that's your final answer. This is the compensator we designed. This is the compensator inside your transfer function. And that's all you got to do.